Hey everybody. Today you can see on your screen we're going to work our way through what I'm going to refer to as some special factoring. Really what it is we've been working our way through and we've learned how to do some common factoring with multi-term expressions. We've been able to factor some simple trinomials. We've worked into some complex trinomials. Now we're going to deal with some quirkier stuff. We're going to address two big areas, though, that we want to be very, very comfortable with, but then we're going to work our way into some puzzle-like problems. So we've got a lot of stuff to cover today. Let's jump right in. You can see on your screen right now 3 problems, and I really don't want you to focus in on B or C yet. Really what I'd like you to do is I'd like you to focus in on A. And I want to walk through A with you. You should be looking at A and saying to yourself, like, I don't understand why that's a special factor. Like, I've been comfortable to be able to go through and factor an expression that looks like that. And you should be. So I want to make sure that we all understand, I would expect everybody to be able to factor the expression in A. What I want to make sure that we're good with is maybe a way to look at it and especially a way to write it, to express it. So let's take a look at A. If you were to tackle A right now, you should be looking at that term or that expression and saying, I have 3 terms in it. The first thing I always look for is a common factor, and you notice you do not have a common factor. So pretty quickly then that becomes, okay, 2 numbers that multiply to give 64 and add to give 16. So you could go through all of your processes, your algorithm to be able to figure out what those numbers are. I'm hoping that pretty quickly we can come up with 8 and 8. So if we were to factor that, we may be inclined to want to write x plus 8 times x plus 8, but we should be good with the fact that we should be expressing that as a perfect square. So we really don't want to write down the 2 of the same factor, and we really want to write it down as a perfect square. That's where we're coming in from our background. Okay, all I really want to do is put an idea in your head that when we see a number like 64, we want to try to recognize when we have certain numbers. Like already we recognize when we have prime numbers versus composite numbers. How many factors do we have to try to test? Well, I want to put another idea in your head. Let's look for perfect squares. And let's try to make perfect squares the first part of us for factoring. What I also want to highlight for you is a little bit of a pattern. What you'll notice when we expand our perfect square binomials, that middle term is double what the constant is inside our binomial. Well, maybe we can then tie together the factoring part of that. So if I look at the green and I go, hey, that's a perfect square, 64, then I want to do a quick check and say, well, the square root of 64 is 8. Is my middle term 8 doubled? And when we see that it is, then we can very quickly come right in on our factored form. Okay, so we can see what I'm talking about. Let's take a look at B. You take a look and you recognize you have 3 terms. Leading coefficient is a 1, so it's a simple trinomial. Your eyes go to the 9, and as soon as we see the 9 now, we want to elevate, hey, 9's a perfect square. That's 3 times 3. And then take a quick peek at the middle. Is that 3 doubled? And we say, yes, it is. Then very quickly, we should be good to be able to come in. Hey, I've got a perfect square trinomial. So it's going to factor into a perfect square. We just have to make sure that we've got the correct sign in between, and there we go. Okay. To keep building with that, take a look at C. I want to give you a chance to try C on your own. So I want you to jump in, pause the video, we'll check and see how we do when we come back. Okay, pause it now. Okay, we're back. Well, we take a peek at the very beginning, and maybe now we recognize that we have a trinomial, but it's a complex trinomial because of that 4 out in front. So that shouldn't change the way we tackle it, but it is going to change it a little bit. I'm just going to make a little more room for C there. And as we work our way through on C, now instead of us blindly going over and saying, hey, 2 numbers that multiply to give 4, 2 numbers that multiply to give 5, or 25, sorry. And then maybe we had picked a 4 and a 1 versus a 5 and a 5. Let's try to elevate the first guess and check chart, that fast factoring chart, as opposed to the second one. The same pattern exists. As soon as you see, hey, perfect square, hey, perfect square, now we're starting to think about our fast factoring. Well, if that was a 2 and a 2 and a 5 and a 5, 5 times 2 is 10. Is my middle term 10 doubled? If you're like, yes, it is. Well, then I have a perfect square again. And so I can go ahead and pretty quickly factor that and just make sure I have the correct sign in between. Okay, I'm hoping you take a look at the screen right now and you say, you know what, that stuff was actually pretty usual. It's not so special. If that's the case, then I think you are very comfortable with your factoring. All I want to do is I want to elevate, can we look for perfect squares a little higher in our decision making? Okay, I want to jump into another expression. Let's take a look in the screen right now, and again, you see 4 expressions, but I really want you to focus in on A. Okay, that expression in A was one that we've factored before, but we probably would have looked at it a little differently, and I really want to change the way we address A. This is an important one for us. Okay, if we were to work through A, coming in with what we know, that we would end up looking at that and seeing, hey, there's 2 terms. First thing I look for is a common factor, and I do not have anything in common. So, well, I have an x squared and then a minus 9. I've skipped over my middle term. So maybe we look at it then as saying, well, I've got an x squared plus 0x to kind of force it to be a trinomial. Because then you can go through and deal with your algorithm and say, hey, there's 3 terms. The leading term is a 1, so I have a simple trinomial. And pretty quickly then, you're trying to go through 2 numbers that multiply to give 9 and add to give 0. Okay, then there is my plus 3 and a minus 3. And you now have that factored. You do a quick check, you re-expand, you notice that your middle terms would cancel out, and you confirm that that is now factored. Okay, I want to move away from that a little bit. I really do not want us writing in that green line at all and forcing a binomial to have to be a trinomial for us to factor. We should be able to recognize the expression right in front of us. To do that, I want to erase that green line and imagine it never existed. Okay, at the very top, we have an expression that is referred to as a difference of squares. And that's the name of that expression. Now, it is not a puzzling name. There should not be a part where you look at that and you go, I wonder, why is it called that? Take a look at your expression and you will notice it is literally its name. Look at the first word, difference. Difference means subtraction as an operation. There's your difference. Look at the next part. Squares. Well, look at the first term. It's clearly a squared. It's x with a square on it. 9 is a perfect square. So the expression x squared minus 9 is literally a difference of squares. There's the name. For us to make sure that we can recognize difference of squares as a type of expression. Then when we factor a difference of squares, we actually get a pretty special type of form. This is something that is called conjugates. And what conjugates are the same terms with your factors, but different signs. So you'll notice both of your factors start with an x, both of your factors end with a 3, and each of them have a different sign in between. One a plus, one a minus. That's what we refer to as conjugates. So it is important for us to denote conjugates expand to give us a difference of squares. Difference of squares factors into conjugates. And if we can add those two terms or phrases, then we now have a new form of an expression that we can factor, and one that can actually get pretty ugly at times. But being able to factor a difference of squares into conjugates is going to become so important, so useful. So I want your focus now to be on the expression in B. Let's take a look at B. Yes, you could go ahead and force it to be something else, but we don't want to. We take a look at B and we start to go down our checklist. What's the first thing I look for? I look for a common factor. I don't have one. Since it's two terms, hey, this might be a difference of squares. Well, I now take a look. 144 is a perfect square. That's 12 times 12. And m squared is a perfect square because, duh, look, the squared. So if I was to factor that expression, I know at the beginning of both brackets, I need to have what multiplies by itself to give me 144. There's my 12. At the end of both brackets, I need to have what multiplies by itself to give me m squared. There's my m. And now, to make sure that they are conjugates, to make sure that the middle terms cancel out, one has to be a plus, one has to be a minus. Of course, it does not matter which factor is a plus or a minus. We just got to make sure we have different signs. You get a little confirmation. Your middle terms are the exact same terms, but opposite signs, so they cancel out. And you get a little extra on the plus and minus, so a positive times a negative confirms that we get our negative in between. There we go. Okay, we want to make sure that we add a difference of squares to the sort of expressions we can factor. Okay, what I want you to do is I want you to go ahead and try both C and D. Okay, I want you to try both at the same time, or obviously D after C. But you work your way through, factor those, we'll come back and we'll check and see how well we're doing. Okay? Pause the video now. Okay, we're back. So you take a look at C. I have two terms. First thing I look for is a common factor, nothing in common. So now I examine both those terms to see if they're a perfect square. And they are. Difference of squares. But each term is a perfect square. The first term, 4y to the fourth, that is a 2y squared all squared. Notice 4y to the fourth is 2y squared times 2y squared. 81m to the fourth is also a perfect squared. 81 is 9 times 9. M to the fourth is m squared times m squared. So I have a difference of squares in the expression in C. Okay, what goes at the front of both brackets? What goes at the end of both brackets? And I have to make sure one's a plus, one's a minus, just for the sake of making sure that you don't think there has to be a way. No, I'm going to change the signs. There you go. Okay. I think if you were able to go through and factor C, then you're doing great. I want to talk to you about D, because I do think that a lot of us are going to make a mistake, and it's going to be a super common mistake. So let's make sure that we knock it out of the way at the very beginning. You should not have been able to factor D. And I promise I'm not going to do this to you a lot. I feel like I threw a bit of a trick question at you. I asked you to factor an expression that you can't factor. But I would have had a number of people go ahead and factor D as a difference of squares. Just kind of looking and going like, okay, well, 25 is 5 times 5. Y squared is y times y. 16 is 4 times 4, so there's a 4 and a 4. And you either made one of two mistakes. You did this, made one a plus and one a minus. That is incorrect. Just to make sure we understand why. If I was to re-expand that and take a positive 4 times a negative 4, I should get a negative 16 in between those two terms, and I don't. The other part, maybe we looked at that and we said, no, wait a second. I recognize that I have a plus in between. So that's got to be my plus. And now I'm going to stop you for a second because we should recognize our mistake. If you're telling me that, then I'm going to have a middle term now. The only way that my middle term, when I expand that, is going to cancel out is if those terms are different signs. But now, if I expanded those brackets, I don't even care about the end on the 16. I'm going to get 40y in the middle, and I can see I do not have a middle term there. So I'm hoping that you can take a look at D right now, and you can tell, oh, wait a second. I cannot factor D. So I'm going to get rid of that blue, hope that you repress the memory of ever seeing that. And really what I want to put in your mind is make sure that you're good. There is no such thing as a sum of squares that is factorable. You can't. You can have a sum of squares. That is what that expression is. It's a perfect square plus a perfect square. That is a sum of squares. But you can't factor a sum of squares. Okay. No more trick questions. Okay, so we've covered kind of two topics today. We've factored a perfect square, and then we factored a difference of squares. Okay, I want to put those two expressions in your mind, and now for the rest of the day today, I want to play with some puzzles. So this is where we're going to get into what I would refer to as maybe some of the quirkier stuff. I'm going to call today's expressions challenge problems now. I want you to view them as puzzles, and we're going to try to stumble our way through and factor. There's a lot of little things in these, so please do not get discouraged if we struggle through some of this factoring. I'm going to argue you should, but all we're doing is we're expanding our experience. Okay, I want to jump in and I want to throw two more at you. Okay, take a look at the screen right now, and even though I've thrown two up on the screen, do not work through both. I really want you to focus in on just E. I want you to struggle on E if you need to, okay? What I want you to do is I want you to work your way through on E on your own, and we're going to see how well we do, okay? Pause the video now. Okay, we're back. So, I would guess that I would have a bunch of people that were able to factor E. And actually, you probably had very little difficulty with it. That is, you took a look, you said, I have two terms. There is no common factor in both terms. So then you check and see, is it a difference of squares? Very quickly, you see you've got a minus in between, so there's a chance. Then you take a look at both terms and you say, hey, they are both perfect squares. X to the fourth is x squared times x squared. 1 is 1 times 1. I have a difference of squares and I can factor. Okay, I would have expected a lot of people to give me that. Now, maybe you have them in the opposite order. We know that's the exact same thing. Okay. Here's our problem, though. That's not fully factored. Now, I would 100% agree that green is factored, but it is not fully factored. Take a look at the first factor, x squared plus 1. Can you factor that further? And I'm hoping you can look at it and say, no, I can't, because you just covered there's no such thing as the sum of squares. And I'm like, you are exactly right. But what about the second factor? And I'm hoping you look at that red one that I've denoted and said, oh, shoot, I have another difference of squares. So I'm going to get rid of those stars. We can actually factor that expression further. I cannot factor x squared plus 1 any further because there's no such thing as a sum of squares to factor. But x squared minus 1, that is another difference of squares. It would factor into an x plus 1 times an x minus 1. So all that ended up happening was we were able to take the expression and break it up into something times something. We couldn't touch the first something, but we were able to factor the second something further. Okay, if you were able to get down to that last line, then that is outstanding. If you got the first line, then you prove to yourself you can recognize a difference of squares. Now the trick becomes, okay, every time we finish factoring a problem, we got to take a look and see, can we factor further? Okay, I want you to do the same thing on F now. I want you to go ahead and try it on your own. Okay, pause the video now. Okay, we're back. I'm just going to put a little wavy line down the middle. We take a peek. I would have had a number of people that would have done this and said, I'm not sure where to go, but I am really good at expanding. And we have already spent time on previous days going through and talking about when given the instruction to factor, do not expand. You're going in the opposite direction. But I would have had some people that then would have gone through and done all of this pink. And I would say to you, no problem. Good job. You've got it factored. There's your last line. Okay, but I don't want you to factor that expression that way. But it's totally fine if you did. It just seems like a lot of work. So instead of going in the opposite direction, expanding, why don't we just factor directly? So I'm going to get rid of all that pink. Okay, if I take a peek at F right now, we should be good to see you have two terms. It's just that your terms are getting a little uglier. Like my first term is okay, it's just my 16. My second term is getting a little uglier because now it's made up of two terms. It's a binomial. But because of those brackets around it, it's really just one term. Hey, I have another difference of squares. Now, I would love it if we could factor it directly. But if we're struggling to see that that is a difference of squares, I could say that I was going to let x plus 2 equal something else. And now that expression would look like that, the blue, and I'm hoping we can recognize our difference of squares. So if I was to factor the blue would factor into a 4 minus a times a 4 plus a. Hopefully we can see how that factored. We're okay. The problem was I didn't give you an expression with a's in it. I gave you an expression with x plus 2's in it. So now we would have to re-substitute back in. Okay, I don't want you to have to use substitution. I would hope that if I get rid of that blue, we could factor that efficiently at the very beginning. My advice to you, though, would be, as things start to become a little uglier, maybe don't use round brackets. Let's put in big square brackets so we can see something. Okay, if I recognize that that is a difference of squares, then maybe I'm not going to write that out left to right as we've been going through the last couple, but instead, I'm going to go back to the way we started. Look at your first term, 16. What multiplies by itself to give you 16? 4 and 4, that's at the front of both brackets. Okay, now you take a look at the second term. What multiplies by itself to give you x plus 2 all squared? Well, that's an x plus 2 times an x plus 2. That goes at the end of both brackets. Now you need to make sure one's a plus, one's a minus, and you're good. Okay, if you have that goal down, you're doing really well. It's wrong, but you're doing really well. There's a little bit of a hiccup that we made, and it's the common mistake. And it all stems from your second term is 2 terms. That second perfect square is 2 terms. It's an x plus 2. So when you add the second thing, we should really have brackets around there. Now, does it matter if I have those brackets? Well, no. If I'm going to add something, then I add it. Whether it's positive or negative, it's no change. But look at my second bracket. If I subtract something, I didn't subtract the whole x plus 2 unless there's brackets around it. Those brackets are necessary. They're necessary to make sure that I subtract all of the x plus 2, not just the x. So I'm going to get rid of all of that red that I just wrote in. That isn't necessary. What you see on your screen now, that would be needed. Okay, now all I need to do is just clean up each of those factors, simplify them. So, in my first bracket, I would have a 4 plus an x plus a 2. Well, then that's an x plus 6. And in my next bracket, I would have a 4 minus an x minus a 2. So I would have a little collecting to do there. And rather than writing this as a negative x plus 2, we would consider that bad form. It's bad form because we wrote it with extra operations that aren't needed. See that negative out in front of your x? What that means is if I change the order I write those, then I can write down fewer operations. So rather than writing that as a negative x plus 2, I'm going to write that as a 2 minus x, and now that is simpler. And there you go. Okay, if you were able to get down to that, then I'm not challenging you enough, and we need to play around with some more puzzles. But I'm hoping that by going through E and F, I've built up an extra instinct in you that now we can deal with factoring further in E and factoring more complex difference of squares like you see in F. Okay, let's keep going with the puzzles. Okay, you take a look right now at G and H. And I want you to tackle G only. Okay? So Pause the video and give it a shot. Okay, we're back. So you're playing around with something like G, and you say, hey, wait a second. We've dealt with this before. I have a 4-term expression. First thing I look for is a greatest common factor. There is no common factor in all 4 terms, so we look to group it. And maybe what I do is I group it 2 and 2. Well, if I try to group the first 2, I could pull out a common factor of x. And if I try to group the last 2, hey, wait a second, that's a difference of squares. That's a 3 plus a 4y times a 3 minus a 4y. Hey, look, I was able to factor that. And we got to stop because that's not factored. Remember that the only way that that is factored is if it is one term, as if it's written only in multiply, and that addition symbol in between is stopping that from being factored. Yes, you did some factoring, but the expression is not factored. So you would now be looking at that pink and saying, I have one term and another term, so I have 2 terms. Now can I factor that? And you notice you can't. Shoot, we went down a path we can't get back from. Okay, that method did not work for us. So then what? Well, I'm going to get rid of all of that stuff and go back to the beginning. Well, rather than us trying to factor by grouping, and by grouping 2 and 2, then maybe there's another way we could factor. Maybe there's another way we could group. And there is in question G. If we took the first 3 terms, and you might notice that those first 3 terms took a common form. You had a squared something, a single something, and a constant, and they all had x's. So there is my simple trinomial. And then I've got the y term on the end that's kind of not like the others. Well, if I grouped my first 3 terms together and I tried to factor that, well, I can factor that pretty quickly. Hey, 2 numbers to multiply to give 9, add to give 6. That's a 3 and a 3. And we end up writing down that expression. Okay, you will notice that that is not factored because you've got that minus in between. So you still have 2 terms. And then you go, but wait, I just got myself into the same problem I was in before. I don't have a common factor. I can't factor that. And here's the key with how we write some things. When you take a look at that green and gold right now, I would agree, it does not look like it factors. But I'm hoping you recognize I did not write my green in a good form. That was x plus 3 times x plus 3. I should have written that as a perfect square. And if instead, when we factor it, we write it in good form, I want you to take a look at my green and gold, and you should notice you can factor that further. Okay, I think I may have caught up with some people, and I want to give you another chance to be able to factor that. So I want you to pause the video and try to see if you can finish that one off. Pause it now. Okay, we're back. So I'm hoping that we recognize that what you have in G is a difference of squares, and we are able to factor that into conjugates. So to be able to do that, I should be good to say, well, I'm going to put in my big square brackets. What goes at the front of both brackets is an x plus 3, because that's what was squared. What goes at the end of both brackets was a 4y, because that's what was squared. And if I'm going to factor it into conjugates, one has to have a plus, one has to have a minus. Okay, There's really no inherent way that we should write that in terms of form, but you will see a common way of it being expressed would be to put your variables in alphabetical order with your constant on at the end. Do not worry about the green. If you gave me the blue, you are perfect. You just might see it more often than not written in the form of the green. Okay, I'm hoping we added in another strategy for us. Hey, if I have 4 terms and I can't find a common factor, then I don't only have to group 2 and 2. I can try grouping 3 and 1. Okay, I think I've caught up with you again. Let's give H a shot. Okay, I want you to pause the video, try that one on your own. Okay, pause it now. Okay, we're back. So I am thinking that given what we just talked about in G, I would have a lot of you inclined to see that 4-term expression, look for a common factor, there isn't one in everything, group it, and maybe we even skipped over the grouping 2 by 2. But if we went to try to group it 3 and 1, well, grouping those first 3, that's not going to help. So maybe we played a little game of one of these things is not like the other. How could I group it 3 and 3? Well, I notice I've got a squared M term there and then a single M term. If I threw in the constant, that would make it a trinomial. Wait a second. Maybe this N term is the one of these things that's not like the other. So if I rewrote that expression and all I did was rearrange some things, put that 64n to the 4th at the end, then maybe we see we have something similar to G. Okay, can we factor the first 3 terms? Well, I'm going to take these first 3 and factor them. It's a complex trinomial, so when I go to factor, 2 numbers that multiply to give 9, 2 numbers that multiply to give 2. There's a 6, doubled 6, that does give me a 12. I need to make sure I've got minuses in between. So I get a 3m minus 2 times, no, I'm going to stop myself. I'm not doing it. Because it's 2 of the same thing, I'm writing it as a perfect square. That leaves me with my last term of a 64n to the 4th, and I notice I've got another difference of squares. And so now I can go ahead and I can factor that further. Okay, I'm going to put in my big square brackets just to make it a little easier on myself. What's being squared to give me the first term? 3m minus 2. At the end of both brackets, what's being squared to give me 64n to the 4th? Well, 8 times 8 is 64, and n squared times n squared is n to the 4th. Okay, to make those conjugates, different signs in between, and we are good on our order. There you guys go. Nice. Okay, I think we keep expanding what we're playing around with. Let's keep it going. Okay, so let's take a look at both I and J now. And I think we should be good to be able to work our way through both of those, or at least get started on them both. So I want you to be able to work your way through. Let's start off on I. Pause the video now. Okay, we're back. Okay, I'm going to discuss the solution to I like we've got a lot more background to it. We take a peek, 4 terms, no common factor in all 4. We try to group 2 and 2. Maybe that doesn't work. So now we take a peek and we notice we've got this 2AB term. That's a term with both an A and B in it. What that means then is we probably can see that as the middle term between both the A term and the B term. And if I do rearrange my expression that way, then pretty quickly we should see that my first 3 terms is the trinomial that would be A plus B all squared expanded, right? 2 numbers that multiply to give 1 and add to give 2 would be 1 and 1, and so there's my factors. I'm going to get rid of writing down those 1s because that's horrible form. There we go. Now, I still have that minus c squared on the end. We should be pros now at being able to factor this, so much so that I don't have to write it with the big square brackets. Like I could just go, okay, so I know at the front of my bracket is going to be an A plus B. At the end of my bracket is going to be a C. I need one of them to be a plus and the other to be a minus. And we can just write out those factors left to right. Okay, I think your doozy is question J. I think J is probably one of the hardest expressions that I will ever throw at you to be able to factor. So I want you to pause the video if you hit a snag earlier, and I want you to give J a shot again. Okay, pause it now. Okay, we're back. So why do I think J is uglier than the previous? Well, you notice it kind of plays the same way. Like I've got this term that's made up of B's and C's. So if I'm going to go through and try to factor that expression, then maybe I want to put the B's and C term in between the B squared and the C squared term. So all I did, I just took my BC term and I wrote it in between, lining up my trinomial. Well, now I can go ahead and I can look to factor that trinomial. Except here's my problem. That's not a perfect square trinomial. Now, it not being a perfect square could jump out at you in a number of different ways. Maybe where it jumps out at you first, that last term is negative. If that's a perfect square trinomial, I need that last term to be a positive. The same things multiplied together. Okay, but maybe the other spot to identify, my first term is negative. So what I need to make sure I'm good with then is dealing with how can I make that a perfect square? Well, the one thing to note, take a look at that big ugly brace bracket that I wrote down in pink underneath. If that brace bracket was to surround my one term, I would need to put brackets around that term. And as soon as I go to put brackets around that term, notice I just changed the value. Now if I was to go through and expand, all of a sudden my signs are different. Okay. How can I tackle those last 3 terms? I actually need to factor out the coefficient in front. So if I pull out a common factor from all 3 of those terms on the end, then you notice you've now changed those last 3 terms into a trinomial, and you love seeing that last term with a plus. Okay, let's see, does that trinomial factor? Well, my first term is 9b squared. That could be a 3 times 3. My last term is 25c squared. That could be a 5 times 5. And if I check, 15 and 15 does give me 30. So if I were to factor that expression, that would be a 3b minus a 5c all squared. Okay, how can I factor that now? Well, we should be pretty good. I'm going to tack in everything. So if I go to factor this one, I'm going to put in my big square brackets because the common mistake could pop up. Okay, what's squared to give me my first term? A 2a times a 2a. What is squared to give me my last term? A 3b minus 5c. Now that my second term is multiple terms, I want to put brackets around. I did not need those brackets for when I add, but I absolutely need them for when I subtract. Okay, clean up your factors. So I can eliminate those red brackets in the first and eliminate them in the second. That will have an effect, a change, and there we go. Okay, I think if you were to look back on all the factoring problems we've done today, I think that becomes your doozy. And maybe you can see why I consider J to be one of the most difficult factoring problems you'll see. Okay, I want to tackle two other problems, but that's the end of just straight factoring problems for us. You really need to spend time jumping in and working through all the different types of expressions to factor. They're all going to get jumbled up for you on an evaluation. So we have to make sure that we can address them all as puzzles and work our way through. Okay, let's change gears and tackle a different sort of problem. Take a look at the screen you have in front of you now, and you'll notice I've changed your instruction, evaluate, and I gave you like this weird looking problem. There's no variables. Like, what am I? Okay, just take a look at this expression. I wanted to throw this one out there so you can see how sometimes recognizing things as a difference of squares can be really useful to you. If I was to ask you to evaluate that expression, 101 squared minus 99 squared, and I said you don't get a calculator, I would have a bunch of people in here that are going to take so long, and you would look at that as like a horribly difficult question because you're going to spend all this time calculating 101 times 101 because it's not like you memorized that, and you're going to calculate 99 times 99 because you don't memorize that. That's going to take forever. But if we recognize that 101 squared minus 99 squared is a difference of squares, then maybe to evaluate it, what might make it easier is to factor it first. Well, if we can recognize that that does factor, and it factors into conjugates, 101 plus 99 times 101 minus 99. Well, now I can collect that. Really, look at my first bracket. 101 plus 99 is 200. Look at my next bracket. 101 minus 99 is 2. And if I multiply those together, I just answered my problem with no calculator. Now, I know a lot of you are going to believe your calculator more than you'll believe me. So go ahead and punch in that expression at the very beginning. Confirm you get 400. But you now have a way to tackle maybe some different expressions without a calculator. Nice. Okay, keep that in your back pocket. That can be useful from time to time. Okay, I want to play around with one more problem. I'd like you to take a look at problem 4. And I want you to give problem 4 a read. Okay. What value of k will make 4x squared minus 12x plus k a perfect square trinomial? Okay. What value of k will make that a perfect square? So I want you to play around with that problem for a little bit. This is a chance for us to steal some problem-solving practice. Okay? I want you to give it a shot. See what you can come up with. We'll come back and we'll talk strategy. Okay? Pause it now. Okay, we're back. So I want to talk strategy on a problem like this. The problem says we got to make it a perfect square. So we should be good then that the perfect square means something squared. Okay, you should tie together that if you have a trinomial like this, then if we were to expand a perfect square and it gives us a trinomial that follows that pattern, then it must have come from a binomial base. So what we're looking for then is, okay, what two parts to that binomial would expand to give you 4x squared minus 12x plus k? Okay, a couple things to consider. If it is going to be a perfect square, then it's got to be something times itself. Let's zero in on the first term. You know your first term. When we expand that bracket, it's got to give you 4x squared. That tells us we can confidently say that our first term in our bracket has to be 2x. 2x times 2x gives me 4x squared. What we can't say confidently is what gives us the last term, because we need two numbers that multiply to give k. Those two numbers have to be itself. But because it's a k, we don't know what that value is. Okay, how can we play around with this? Well, we've also got this 12 in the middle. Okay, what would this look like if we expanded? Well, I have an algorithm for expanding. I'm going to just plug something in to help us out here. I'm going to put like happy face in, so we recognize it's just something missing. If you were to expand that red happy face expression, then you would say that you would take 2x and square it. That gets us back to the original. That's good. You would then multiply those two together and double it. So you're going to get 2 happy faces, x, doubled, which would then give you 4 happy face x's. So notice that middle term of 12x, or more specifically, negative 12x, is something doubled. So really what I want to do then is I want to take that negative 12x and I want to take half of it. If I know it came together by being doubled, then to go backwards, I'm going to take half. And if I take half of that, then that's a negative 6x. Okay, I'm just going to get rid of my happy face stuff so we don't get confused by it. What that tells me then is when I take my 2x and I multiply it by something, that has to give me negative 6x. Well, 2x times what gives me negative 6? Well, I've already taken care of the x part. I've got it there. I just need the number. So 2 times what gives me negative 6? That would be my negative 3. Now I get a little confirmation. Let's expand it and see if we get back. Okay, we take a look at that perfect square. And now to get that middle term, 2x times negative 3, that's a negative 6x. Doubled gives me negative 12. Perfect, I'm good. So the question asked me what value of k makes that a perfect square. In order for me to figure that out, I would have to expand. So I need to take that negative 3 on the end and fully expand that bracket. I'm hoping we can see that it's a k value of 9. Let's give it a quick check. Expand the first, so square it, multiply those together and double it, square the last, and we get some confirmation. There is your k value. Oh, nice. That one's a bit of a doozy too. Okay, your job. Work through all of that practice that we've done by adding in some of this special factoring. Make sure we're comfortable factoring perfect squares and a difference of squares. And then we got some problems on at the end that give you a little bit of a quirky sort of thing. Hey, some fast mental math, as well as some missing values, some K questions. Okay, your job, jump in and get some practice. Make this fluent. Okay, good luck.